Hello, hello. How's it going, everybody? Hope you're all doing good. Let me fix my hat here. There we go. How's it going? It's a little warm and toasty. Let's take this little overlayer off. Hope you guys are doing good. I'm still getting a little bit organized here. Give me a second. Here we go. All right. Cool. Let me go ahead and let the Discord know that we are live. All right. All right. General Sox, welcome back. Right on time. How you doing? Hope you're doing real well and hope all's going well with you. How's it going? Edwards, good evening. Welcome back. It's so awesome that you came back and it's so awesome to hear from you. How are you doing today? Welcome, welcome. All right, this is going to be a little bit of a shorter one. I am not going to lie. I have to drive a little bit to catch a flight early tomorrow morning. So I'm spending the night in a neighboring city, just with my girlfriend, and then we're catching a flight. So um, for the holidays, but I'm going to try my best to stream over the holidays. I'm going to do my best to hop on for at least an hour and a half, each day still, and keep the streak alive. So um, I'm committed if you guys are. So awesome. All right, without further ado, because this is a shorter one, let's go ahead and just jump right on in with the problem. So we are back in data structures and algorithms in Python for December the 23rd, 2024. 2 days till Christmas. 2 days, for me at least. For some of you, it might be one already. It might be Christmas Eve for some of you guys, which is crazy. Merry Christmas Eve if it is Christmas Eve for you guys, and if you guys celebrate that, and if not, then there's happy holidays, and hope all is well for you guys. I hope everyone's safe. Let's just jump right on in here. All right, boom. All right, experimentally evaluate the efficiency of the pop method of the Python's list class when using varying indices as a parameter, as we insert for on page as we did for insert on page 205. Report your results akin to table 5.5. Okay, so on page 205, let's go back up here. So this is page 204, 205 here. So what do we do? As we did for the insert on page 205, okay. Experiment to evaluate the efficiency of the pop method of Python's list class when using various indices as a parameter, as we did for insert on page 205, akin to results in table 2.5.5. Okay, so what we need to do is Domino. Hello, how you doing? It's so awesome. How you doing? Welcome, welcome to the stream. I'm so glad you made it in. So for this one, we're going to need to, for n in range n data dot pop. So we're gonna pop. No, so that's inserting. So we need to pop how many times? So let's say we have a list here. We have a L is equal to some list of values of none times 100. So that creates a list with none times 100 nuns inside of it, 100 values of none, and we're going to pop off values. Um, so from import time. Hey, Script Serpent, welcome back. So we need to import time for this problem because we need to track time, right? Oh, this one's just going to take us too long. I kind of want to skip this one for right now and come back to it when we have more time in a stream. I don't want to burn our entire stream working through this one. This one's just not that entertaining, really. We're just kind of proving pops. Play Code, how's it going? Welcome in, how's it going? For n in range. So we say for data in the range of 100. Okay, so we got to go like this. Big N, actually. So we'll go like this. And then we'll say data.pop n. We need we obviously need a list, an array of data equals so let's give a function here, def time pop, which takes in some value of n. So n is equal to an integer, and we're going to return a like a time, like a float. I don't even know. So we take data, we will do data none times n, right, is provided like that. And then for enemy pop, but we need to time the values here, right? We pop all right. How you guys doing today? Okay, so we're going to fill in the data with the integer n. For n in the range, we're going to pop it at, so we need to time this. How do we use the time? I forgot. How do we use time? Was it chapter 3? Notes. Time takes timestamp. Time it. Time. Hey, Larry Goodman, welcome in. How you doing today? Good evening to you. The time function complement and time module is used to get the current time in seconds, and this is value. You can use time before and after the book to measure how long. Okay, so we're going to call the time function right here. we're going to end time is equal to the time here. We're going to return start time minus, right? No, end time minus start time, rather. So we're going to pop all the values of n in our whole data place. So I think this will work. Now we need to do this at k equals 0. So we're popping at varying indices as a parameter as we did. So we're going to first pop at the n, right? So at the end. So just calling pop normally. If we pop, no, we don't want to pop n. We want to just pop, right? And this will just say like that. Okay, so now if we call this, let's go print time pop for 100, right? Oh, no. Time. Okay, we need to say from time import time, that's right. Okay, so that's the time we got back for popping 100. How are we gonna do this? Let's just go like this. 100, 1,000, 10,000, 100,000, 1,000,000. Like so. And then we'll go over to this block here and make this k equals 0, k equals n floor 2, and then this is equal to k is equal to n. And then let's go ahead and let's just bring these out like so. Okay, so for 100 items in the k is equal to n, we get 4.05 e to the negative 0.06. Like so. Okay, now what if we do pop for 1,000? We get 1.9 what did I do? 2 decimals lessons. 91 e to the negative 5. Cool. Now what if we do pop for, let me make my screen a little bigger here. We do pop for 10,000. Hey Tim, how's it going? Welcome in. We're just solving this problem here. We get point. So it doesn't make sense that our time is getting it's getting larger, right? This is smaller. Okay, our time is just increasing because we're increasing obviously integer size. So this is making sense somewhat. Okay, now this is 0.00023. And then 10,000 or 100,000 boom, would be 0.0023, and then a million would be 0.018. Cool. Nice. Hopefully we're doing this right. We're getting values here which are making sense. We are increasing in time as we have to add and pop more values off, right? We're popping a million values here. So now let's say we need to, let's go reset our function back down to 100. But now instead of popping at the n value at the end of the function, we need to pop at 0. So, right, pop 0 pops index 0, right? Yes. Okay, sweet. Okay, so now we need to pop at 0, where k is equal to 0. Okay. Ooh. And now let's go and run this. For 100, we get here k equals 0, 6.91 e to the negative 6. We get, hold on one second, you guys. Try this real quick. Hold on one second. All right. How you guys doing today? All right, let's keep going here. 1,000. 9.49 e to the negative 05. For 10,000, we get 0.0068, right? For 100,000, oops, we get we get different values each time. We'll take this first one that it gave us. 0.693 1, and for a million, 0.697 5. Okay, now we need to pop at the middle. So pop at so we'll pop at the length of data divided by 2. So this will pop at the middle, about. And now we'll reset this back to 100. Now for 100, for this one we get 6.20 e negative 0.6. For 1,000, got 0.0001. For 10,000, we got 0.0038. for 100,000, 0.0034735. And then for a million, 0.342 or 347.2. Okay, so what is this graph? What is this telling us now? Okay, we solved these problems. Cool. Now what is this telling us is that, right, when we're popping the fastest, the best, or, when we're doing a pop of just the length, that would be the fastest time where we don't have to shift anything. We can just take the last element off. We pop off the last element. So our fastest function should be this one right here, which is true. See, meaning that we pop off 100 elements should be our fastest. Then it should get increasingly slower, right? Increasingly slower, and like our time it takes should go up as we append more or pop off more items. For popping at the half point, we add a little bit more time here. Our time gets pretty and starts drastically kind of getting bigger here for bigger items, and when you have to go half point. But then you have to go all the way to the when you have to go all the way to the zero index, you can see here you like drastically have to change the amount of time it takes to do large input sizes. So I'm gonna take this, go here like that. Okay, let's see what it says about our problem here. The experiment investigates Python's pop method when removing elements at different positions k in a list. This aligns with how Python's list implements a dynamic array, which affects performance based on the position of the elements being removed. So these are our k values that we are popping at. Right, so then this is just our chart populated here as such. Is my implementation correct? Your implementation is mostly correct, but there's a subtle issue regarding the list data is modified during the pop operations. After each call, the list decreases, so the middle index dynamically changes. Behavior might not align with your intended test, fixed indexes, or specific sequences. To ensure proper evaluation for a static sequence, you should use a fixed size list in every iteration if desired. Oh, okay, so it wants us to make a list. Wants us to make a list. Okay. Length data. Data is initialized out front. So we are taking the length of the additional data list. I think this is fine. Okay. Cool. Awesome. That was that problem. We solved that one a lot faster than I thought we would. Honestly, that I think we're really, this just proves that we're really making strides in understanding this material, right? You guys, it just I'm able to solve these problems on these, try it yourselves more and more quicker on my own, like, right? All right. R 5.9 underscore key dot pi. 1, 2, 3. Okay, let's try one more problem here. Explain the changes that would have to be made to the program of code fragment 511 so that it could perform the Caesar cipher for messages that are written in alphabet-based language other than English, such as Greek, Russian, or Hebrew. Oh gosh, the Caesar cipher I was struggling with. 511. Okay. Explain the changes that would have to be made so that it could perform the Caesars for written in alphabet-based languages other than English, such as Russian, Greek, or Hebrew. Um, what? Explain the changes. Okay, so what's going on in this program is that we are creating an encoder and a decoder, which is just our way of solving the riddle pretty much. Um, hey, 1, 2, 3, 4, 5, 6. Yeah, this is an online book. It's called Data Structures and Algorithms in Python. We've been reading it aloud on stream, and so you can either look it up online, or I also provide a copy of the PDF in my Discord link below, where I just have conglomerated all my study resources I am doing on the stream down below. Thanks so much for joining today. How you doing? Okay, let's go ahead and I just don't want to do these Caesar cipher ones right now, and we don't have a lot of time. We only have about an hour more until I have to head out. Unfortunately, it's going to be a short stream today. I still wanted to just get on and do a little bit of notes, or a little bit of practice here. What page did we leave off on for chapter 6? We left off on I think we left off on here. Doing good. Also starting Python soon. I'll join the Discord in a bit. Oh, great. Awesome, man. Thanks so much for coming in and for chatting with me here. That's awesome. Okay, matching parentheses and HTML tags. Okay. 6.1. In this subsection, we explore two related applications of stacks, both of which involve testing of pairs of matching delimiters. In our first application, we consider arithmetic expressions that may contain various pairs or of grouping symbols such as parentheses, braces, and brackets. Each opening symbol must match its corresponding closing symbol. For example, a left bracket must correspond to a right bracket, as in the expression 5 plus x minus y plus z, right? The following examples further illustrate this concept. We leave the precise definitions of matching groups symbols to, okay. An algorithm for matching delimiters. An important task for processing an arithmetic expression is to make sure their delimiting symbols match up correctly. Code fragment 6.4 presents a Python implementation for such an algorithm. A discussion of the code follows. So we have def is matched, which takes in some expression, returns true if all delimiters are properly matched, false if otherwise. So lefty equals all the left hand symbols, righty equals all the right hand symbols. And then we call a stack, we call a stack array from our stack array function, okay, or class. For every character in our expression, if the character is a lefty, we want to push it onto the stack. If the character is a righty, we want to, if the character is righty and the stack is empty, we return false. If righty.index character it does not equal lefty.index, return false. Okay, so We assume that the input of a sequence of characters such as this, like some expression. We perform a left to right scan of the original sequence using a stack S to facilitate the matching of grouping symbols. Each time we encounter an opening symbol, we push that symbol onto S. And each time we encounter a closing symbol, we pop a symbol from the stack, assuming S is not empty. Each time we encounter an opening symbol, we push that symbol onto the stack. Each time we encounter a closing symbol, we pop a symbol from the stack. Okay, assuming that it's not empty, and check that these two symbols form a valid pair. If we reach the end of the expression and the stack is empty, the original expression was properly matched. Otherwise, there must be an opening delimiter on the stack without a matching symbol. Okay, I got you. So what this is doing is um, uh, it's scanning our expression. See, as if, for example, this is our expression, right? It's going to start scanning our expression from left to right, and when it comes across a lefty delimiter, right? Um, right? Delimiter, is that the right word? Yeah. When it comes across a lefty delimiter, it's going to push it onto the stack. So it's going to push the left bracket, the left parenthesis onto the stack. When we get to a right hand value, we're going to pop from the stack, assuming that, and then check to make sure that those values match up. So, right, this one gets pushed. Or, come on. The bracket gets pushed. The parenthesis gets pushed. Right? All right, we found a righty. We pop the righty. And we pop the lefty and check to make sure it equals the righty. It does. Boom. We push this one. Now we pop it back out, and now we pop the other one back out. The left hand. Okay, cool. We assume that input a sequence such as this. We perform a left to right scan of the original sequence using a stack S to facilitate the matching of grouping symbols. Each time we encounter an opening symbol, we push that symbol onto the stack. Each time we encounter a closing symbol, we pop a symbol from the stack, assuming it's not empty, and check that these two symbols are a valid pair. If we reach the end of the expression and the stack is empty and the original expression was properly matched. Otherwise, there must be an opening delimiter. If the length of the original expression n is n, the algorithm will take at most n calls to push and n calls to pop. Those calls run in a total of O of n time, even considering the amortized nature of the O of 1 time bound from these methods. Given that our selection of possible delimiters has constant size, auxiliary tests such as C in lefty and righty.index C each run in O of 1 constant time. So what is stir.index C? Stir index C method is used to find the index of the first occurrence of a specified character of the substring of C, of substring C in string. The character, so okay, it just returns the index that the first occurrence is found. So if we call, if the index that's returned righty.index this popped value. Okay. So you want to make sure that they equal the same index value of the righty though, or should this be the expression? You're wanting to check that they equal the same. Oh, because the index value would be here. And then the pop would be the same character, but on the left-hand side. You want to check if they're the same. Got you. If they're not, return false. Or if they are not the same, return false. Okay. We got some chats here. Hey, Mike P. Funk, welcome back. Passed my cloud practitioner exam. Awesome. That sounds great. Which is what I would. Awesome. No worries. Yeah, that sounds super awesome, man. Okay. Matching tags in a markup language. Another application of matching delimiters is in the validation of markup languages such as HTML or XML. HTML is the standard format for hyperlinked documents on the internet, and XML is an extensible markup language used for a variety of structured data sets. We show a sample HTML document and possible rendering in figure 5.3, right? So if you know any HTML, we have a body. Within the body is what's on the body of the screen, right? We have a center tag which centers the header of H1 for little boat. We have a paragraph tag which houses our paragraph. We have an open list, an ordered list, which will give us numbered rather than bullet points. Ordered list gives us numbers, right? So we get numbers, and then we have a list, like a list element here, each for those list line, or what is it? List. What does li mean exactly? I know it means like line, like new line for the list owner or whatever. List item probably. All right. In an HTML document, portions of text are delimited by HTML tags. A simple opening tag has a form of quote name, and the corresponding closing tag has a form the backslash name. For example, we see the body tag in the first line of figure 6.3 in quote in A here, body tag. Um, and the matching body tag closes at the close of the document. Other common used HTML tags are used in this example include the body, H1, center, paragraph, ordered list, and list item. Ideally, an HTML document should have matching tags, although most browsers tolerate a certain number of mismatching tags. In code fragment 6.5, we give a Python function that matches tags in a string representing an HTML document. We make a left to right pass through the raw string using index j. What was that? We make a left to right pass through the raw string using index j to track our progress and find the method of the stir class to locate the find method of the stir class to locate the the tag opening and closing characters that define the tags. Opening tags are pushed onto the stack and matched against closing tags as they are popped from the stack, just as we did with matching delimiters in the previous code example. By similar analysis, the algorithm runs an O of n time, where n is the number of characters in the raw HTML source. Right. So this is going to do the same thing, right? We're going to take in some raw HTML document. We're going to open we're going to create a stack using the array stack, right, class that was demonstrated. We're going to save j is equal to the raw.find of this function. So this will find the first character, if any, and return the index value of that. So this is different than the... Hey, Sky! No, 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 no. How is this... Oh, here we go. Stir.find. Stir.find also returns the index of the first occurrence, but if the substring is not found, it returns -1 instead of raising an error. Stir.index, if you expect the character to exist, you want an error if it doesn't. Okay. So find just returns -1 if it's not found. So we use find on this. While j is not -1, meaning that we have a value here, right? We will set k equal to the find for the next instance of this greater than the index value of j, right? So we want to find the closing tag for this one. If k is equal to -1, we return false, meaning that there is no closing tag and this is not a valid HTML. We create a tag is equal to okay, so what we do is we create a string, we save a string as we take a slice of the raw HTML from J where we opened to not including the tag to all the way to K, excluding the closing tag. If not, tag that starts with a, we want to push the tag. Okay, so this just creates those tags. Interesting. Wow. Whoops. Hey, user 8080, thanks for coming in and chatting. Appreciate you coming in. Um, how are you pulling up the ChatGPT on Mac? Is it? Yeah, so you have to just get the app ChatGPT, and then you can just press Option Space, and you can get like a quick hotbar, like a spotlight search. Okay, cool. 6.2 cues. QUE. All right. Another fundamental data structure is the queue, right? Another fundamental data structure is the queue. It is a close cousin of that of the stack, as a queue is the collection of objects that are inserted and removed according to the first in, first out method. A collection of objects that are inserted and removed according to the first in, first out FIFO principle. That is, elements can be inserted at any time, but only the element that has been in the queue the longest can be next removed. We usually say that elements enter a queue at the back and are removed from the front. A metaphor for this terminology is a line of people waiting to get on an amusement park ride. People waiting for such a ride enter at the back of the line and get on at the front of the line. There are many other applications of queues. See figure 6.4. Stores, theaters, reservation centers, or other similar services typically process customers' requests according to their first in, first out principle. A queue would therefore be a logical choice for a data structure to handle calls to customer service center or a wait list at a restaurant. FIFO queues are also used by many computing devices such as network printer or a web service responding to requests. Gotcha. So you just have to stand in line for tickets. It's first in, first out. And then a call center, all the calls come into the queue one at a time, depending on who they on the based on their status and list in the queue, right? All right. Harry, welcome. How you doing today? I'm so glad you were able to make it in. For those of you that are new, my name is Michael. I'm about to turn 26 years old. I'm 25. I graduated back in 2021 with a Bachelor of Science in Human Biology and a minor in Chemistry. And I work as a formulation chemist for a biotech company for the past 3 years. It's been really great, and I'm just, taking on additional skills and really pushing myself independently to learn and teach myself programming, more specifically Python right now, but we'll be diving into other elements soon. If that's something that interests you, like, or in a similar situation, feel free to follow along to the channel. We've been growing really rapidly, and it's been really great to see the support we've been getting. A lot of people are in a similar situation to myself and are seeking maybe some, not really maybe inspiration or just some camaraderie along the way through their journey to know that, it's not all in vain. So we are, in it together, and it's really it's really cool that we have this community growing. So yeah, feel free to follow along. I also have a Discord down below, which I have used to compile all of my study resources, such as the PDF like above, and all of my notes like on the other side of the screen. So feel free to reference those in the Discord below. And also, which is really exciting, is in 2025, so come January 1st, 2025, CS50 is going to be revamping and adding some more material to their CS50X course, which is goes over a lot of different more full stack related processes. And so we're going to be I've been waiting and waiting and waiting for the new material to run out before I decided to launch into that course. And so we're going to launch into it together at the start of 2025. So I will be hosting like some watch parties to watch the lectures together. So I will join the Discord if you want to get in on that. So make sure you have like your account set up in time so we can all do it together and complete it together, like as like a wave of people, like as a group, and it'll be really fun, and it'll be a great way to to do it when to have more and more people there supporting you. It just gives you more and more easy, it becomes easier to do in my opinion. So yeah, that's the plan for 2025 coming up in the next short week or so here. So follow along. We're launching that soon in the Discord. So yeah, so like a couple nights a week on the streams, like maybe like 3 nights a week, we're gonna be taking, having some watch parties over the lectures, and we'll probably be able to complete the course in maybe like a month. I think it would be maybe maximum a month and a half, with the way that we're currently studying and putting in hours. So it might be, I mean, the final project will probably be the biggest part, right? But we could get through all the material fairly fast, I think. So that would be a great time to get through the material yourself and join along. Yeah, I saw him use it. That would be a handy tool to use while coding or anything in general. Yeah, chat, I don't know what to do with HTML. I believe I have a small idea what are the basics. My space days. Hey, I have a Python doc I made that basically covers everything I learned in AWS Python. Is it cool if you want it? Could I post it? That's okay. Yeah, go for it. No worries. Post it in like the Python community or make your own thread in like the Python help and say like, I made this thing for Python, these notes, or yeah, I think in the Discord I've kind of limited the yeah, you could probably throw it in community or in help. I've kind of limited the books to I'm going to convert these over into threads as well to match the layout of the CS50 courses and stuff. So it's coming along here. Discord is we got people showcasing their projects, which is really cool. Chase made this really cool one showing football game scores in the CLI in the terminal, like with like refreshing, which is really cool. So this is a great place to be if you're wanting some support and camaraderie on the channel and everything. Sweet, that sounds great. Yeah, for sure might be fun. Whatever resource will be helpful in the Python community, or maybe make your own. I would like maybe make your own thread in the Python help called like Mike P. Funk's Python resources, and and then just provide them and just keep posting replies to that thread, your thread that you made, and with all of your resources. That'd probably be the best way to do it, I think. Okay, the Q abstract data type. Formally, the Q abstract data type defines a collection that keeps objects in a sequence, where element access and deletion are restricted to the first element in the queue, and element insertion is restricted to the back of the sequence. Sorry, I didn't take in any of that. You guys ever have those moments when you read and then it's just like gone? Like you don't even the line is gone. Okay. Formally, the Q abstract data type defines a collection that keeps objects in a sequence, where element access and deletion are restricted to the first element in the queue, and element insertion is restricted to the back of the sequence. This restriction enforced the rule that items are inserted and deleted in a queue according to first in, first out principle, right? You can only remove items from the start or from the, from the zero index position, and you can only add items from the, or would, for a queue, for a queue, would you, well, it depends on how you would look at the list, right? Would you look at the zero index as the start, or would you look at the popping as the removal of those items, and then pushing is pushing into the zero place for adding to the queue? Because you most likely be, if you have someone in the queue, you're going to have to pop them. So it would be probably be more efficient to pop at the end rather than having to pop at zero index every single time for those values. So if you have someone in the queue, you are going to have to eventually pop them out. So you might as well pop them out at the end of the list, and so make the start of the queue happen at index value zero. What do you guys think about that? Um, for the queue data structure, if an item is in the queue, it will eventually be popped. That being said, would we want to make the quote end of the queue the length of the queue, rather than having to pop at index zero? We would then have to push new data into the queue at index zero. You're absolutely correct in observing that efficiency managing the end of a queue is critical for performance. Let's break down this to clarify why pushing at the beginning and popping at the end isn't ideal, and what a better approach would be. Why pop zero is inefficient. List in Python and implemented as dynamic arrays. When you pop zero, remove from the front, all subsequent elements must be shifted the one element to the left to fill the gap, resulting in O of n time complex. Similarly, inserting at index zero, pushing to the front requires shifting all elements to the right, also n. Why popping from length q1 isn't -1 isn't great either. If we make the end of the queue length q -1 and pop from the back, the actual popping operation is efficient in O of 1. However, inserting at index 0 to maintain the start of the queue still occurs O of n time complexity. The optimal solution is to use append to push new elements to the end of the list and pop 0 to dequeue from the front. Or, for a better implementation altogether, use collections.dequeue or collections.dec. So pop 0 is better than the inverse approach of push 0. Yes, pop 0 is generally better than insert 0 or push 0 for implementing a queue with Python list. Here's why. Cost of pop 0. Pop 0 removes the first element, time complexity O of n, because we must shift, which isn't optimal. It's less expensive than insert 0 for the same size list. Inserts a new element at the beginning of the list, time complexity O of n. Because all elements exist, must shift one position to the right, make room for the new element. Yeah, okay. In a queue, elements are typically enqueued at the end and dequeued from the front. This pattern means that new elements can be added with the append, and removal happens with the pop 0. Using the inverse push to the front with insert 0 and popping from the back requires O of n for every insertion, making it less efficient overall. Okay, so if you're only wanting to take one at a time, I guess it makes more sense to pop at the front at 0 index rather than trying to pop at the end, because you still have to push at the end. So appending just makes it way better than having to insert at 0. Okay. All right. Hopefully that was interesting to y'all. Yeah, join the Discord, guys, if you want some more access to these notes and everything. All right. We've been live for just under an hour here. Let's continue on here. Formally, the Q abstract data types defines a collection that keeps object sequence where elements can be accessed and deleted from the first element in the queue, and element insertion is restricted to the back of the sequence. This restriction enforces the rule that items are inserted and deleted in a queue according to the first in, first out principle. The queue abstract data type supports the following two fundamental methods for a queue. So I need we'll do this. How did I do that one? I did a space. Two, and then we have this, like so, and it was Q's are abstract data types, ADTs, and support the following so 1 Q dot NQ QUEUE. Geez, lots of UEs here. All right, add element E to the back of the Q. Okay. 2 takes Q and does a DQ. Remove. Remove and return the first element from Q. An error occurs if the queue is empty. Okay, the QADT also includes the following support methods, with first being analogous to the stack's top method. Okay. So this goes 3 Q dot first. Return a reference to the element at the front of the queue without removing it. and error occurs if the queue is empty, right? Number 4 is the queue.is underscore empty will return true if queue does not contain any elements, right? And then number 5 is length of queue, which returns the number of elements in the queue. In Python, we implement this with the special len method. Like so. All right. By convention, we assume that all newly created queues are empty, and that there is a priori bound on the capacity of the queue. Elements added to the queue can have arbitrary type. The following data table shows a series of queue operations and their effects on the initial empty queue. So NQ5 adds 5, NQ3 adds 3, the length is just 2, DQ removes 5, empty is false because we have 3 in there, DQ removes the 3, is empty now becomes true, DQ becomes error because we are empty, NQ adds 7, NQ9 adds 9, first references 7 without removing it, NQ4 adds 4, we get the length of queue at this point 3, and we can DQ, which removes the first element added at that point, which would be 7. Cool. Array-based queue implementation. For the stack ADT, we created a very simple adapter class that used a Python list as the underlying storage. For the stack ADT, we created a very simple adapter class that used a Python list as the underlying storage. It may be very tempting to use a similar approach for supporting the queue ADT. We could, in queue elements E, calling append E to add it to the end of the list, but we could use the syntax pop 0 as opposed to pop to intentionally remove the first element to the list when dequeuing. And as easy as this would be to implement, it is tragically inefficient. As we discussed in section 5.4.1, when pop is called on a list with a non-default index, a loop is executed to shift all elements beyond the specified index to the left, so as to fill the hole in the sequence caused by the pop. Therefore, a call to pop index 0 always causes the worst case behavior in theta n time, because of behavior of theta n time. We can improve on the above strategy by avoiding the call to pop 0 entirely. We can replace the dequeued entry in the array with a reference to none. Okay, we can improve on the above strategy by avoiding the call pop 0 entirely. We can replace the dequeued entry in the array with a reference to none and maintain the explicit variable f to store the index of the element that is currently at the front of the queue, such an algorithm would for DQ would run an O of one time. After several DQ operations, this approach might lead to the configuration portrayed in figure 6.5, allowing the front of the queue to drift away from index 0. Okay, so what this is saying is rather than like what we were talking about is when I was asking ChatGPT what was better, it was telling me like why pop 0 was better, but in reality, when we're having that conversation regarding pop 0 versus insert 0 and what the direction of the queue should run in a list, it's actually telling us that it's more efficient to just dynamically keep resizing the queue, and instead of actually removing elements from, and removing them, we can just swap the value. We can take the reference of the element out and replace it with none, and then just have a counter that continually holds the place of the next, technically the new star in the queue. So let's say that you have person A, B, and C line up. Well, we have a length of this queue of 3, right? We have 3 elements in the queue, meaning that, and the A element was the first in method, so it will be the first remove method. A is removed, And but a so we're not going to shrink the length of the list down to 2. The queue remains at length 3, but instead we reference object A. We take that object A reference away and replace it with a none reference, and then have a counter at index now 1 for the B element, which will then be our next item in the queue. So rather than actually, popping and removing the element and then subsequently shifting all the elements down to fill the gap that was popped at index 0, we're going to just swap the reference value with a none and then update the counter for the next element in the queue. That's a very creative approach. Whoever thought of that, that's interesting. Unfortunately, there remains a drawback to the revised approach. In the case of a stack, the length of the list was precisely equal to the stack of the size of the stack. Even the underlying array of the list was slightly larger. With the queue design, we are considering the situation is worse. We're considering the situation is worse. We can build a queue that has a relatively few elements, yet which are stored in an arbitrarily large list. This occurs, for example, yeah, so if we ended up having a queue like that gets very large and then it ends up shrinking down, with we would have a list with lots of nuns in it, like 100 values of none, with only 2 elements next to be dequeued, right? Um, This occurs, for example, if we repeatedly NQ an element and then DQ another, allowing the front to drift rightward. Over time, the size of the underlying list would grow to O of m, where m is the total number of NQ operations since the creation of the queue, rather than the current number of elements in the queue. The design of it would have detrimental consequences in application in which queues have relatively modest size, but which are used for long periods of time. For example, the wait list for a restaurant might have more than 30 entries at one time, but over the course of a day or a week, the overall number of entries would be significantly larger, right? So if you were constantly, you would just have a ton of none values, creating a very large list. At the end of the day, that's just ultimately taking up memory just based on the raw capacity of the list placeholders, right? um, Using an array circularly. Ah, here we go. So if you have items, you can keep the place of the queue and then just keep rotating it once you reach the maximum length of the list. Hey Seth, how's it going? Welcome. Really appreciate you joining and leaving a message. How you doing today? In developing a more robust queue implementation, we allow the front of the queue to drift rightward, and we allow the contents of the queue to, quote, wrap around the end of the underlying array. We assume that our underlying array has a fixed length of n, which is greater than the actual number of elements in the queue. New elements are enqueued toward the end of the current queue, progression from the front at index n minus 1 and continuing at index 0, then 1. Right, so we would, got you, interesting. So the front of our queue is still here. Implementing the circular view is not difficult. When we dequeue an element, we want to advance the front index. We use the arithmetic. The front is equal to front plus 1 modulo n. Recall that the modulo operator in Python denotes the modulo operator, which is computed by taking the remainder after an integral division. For example, 14 divided by 3 has a quotient of 4 and a remainder of 2. That is, 4 and 2/3. So Python 14 modulo 3, or 14 floor 3 evaluates the quotient of 4, while 14 modulo 3 evaluates the remainder 2. The modulo operator is ideal for treating an array circularly. As a concrete example, if we have a list of length 10 and a front index 7, we can advance the front by formally computing 7 plus 1 modulo 10, which is simply 8, as 8 divided by 10 is 0 with a remainder of 8. Similarly, advancing index 8 results in index 9. But when we advance from index 9, we compute 9 plus 1, which evaluates to remainder of 0. So we go back to 0. Oh, so that's where we get the loop, is when we get up to 10 minus 10, or n minus n, or sorry, n modulo n evaluates to index 0, and we start back at 0. Interesting. A Python queue implementation. A complete implementation of a queue abstract data type, abstract data, yeah, using a Python list is in circular fashion is presented in code fragment 6.7, 6.6 and 6.7. Internally, the queue class maintains the following three instance variables: a underscore data, which is a reference to the list instance with a fixed capacity. Underscore size is an integer representing the current number of elements stored in the queue as opposed to the length of the data list. And then the front is the integer that represents the index within the data of the first element of the queue, assuming the queue is not empty. We initially reserve a list of moderate size for storing data. Although the queue formally has size 0, as technicality, we initialize the front index to 0. When the front or DQ are called with no elements in the queue, we raise an instance of an empty exception, defined in code fragment 6.1 for our stack. Cool. This makes a lot of sense. So this is really interesting. So basically you have some arbitrary array large enough to house, the general queue. Elements get added to this queue at index 0. When you dequeue elements, you dequeue an element and then replace it with a value of none, right? And then move the counter to the next element, the front counter to the next element. New elements replace those previous none values, which technically become the back of the queue, or the start of the queue, or the back of the queue, right? Yeah. Interesting. Okay. The implementation of the length and is empty are trivial given knowledge of the size. So the length returns the size, right? And the size determines the amount of objects in there that are not none. So size comes from here initially is 0. We return size, which is 0. Is empty returns size, which is equal to 0. So if we dequeue, we reduce, and if we nqueue, we increase size. So that's how we're determining length. Given knowledge of the size, the implementation of the front method is also simple, and as the underscore front index tells us precisely where the desired element is located within the underscore data list, assuming that the list is not empty. Adding and removing elements. The goal of the queue method is to add a new element to the back of the queue. We need to determine the proper index at which to place the new element. Although we do not explicitly maintain an instance variable for the back of the queue, we compute the location for the next opening based on the formula available equals to the front plus the size modulo the length of data. Now that we are using the size of the queue as it exists prior to the addition of the new element, for example, consider a queue with a capacity of 10 and current size of 3, and a first element at index 5. The 3 elements of such a queue are stored at indices 5, 6, and 7. The new element would be placed at the index front plus size equals 8. In the case with a wraparound, and the use of the modular arithmetic achieves the desired circular semantics. For example, in our hypothetical queue had 3 elements, with the first at index 8, our computation of 8 plus 3 would be 11 modulo 10 would evaluate to 1, which is perfect since the 3 existing elements occupy indices 8, 9, and 10. 8, 9, and 0, right? So the next available Q would, or NQ would be in option 1. The DQ would be on 8. Okay. I need to go back and like reference this wraparound that's going on here with Q's in the notes for sure. When the DQ method is called, the current value of the front designates the index of the value that is to be removed and returned. When we keep a local reference to the element that it will be returned, setting answer equal to self data at index front. Just prior to removing the reference to the object from the list, we assign self data front to equal none. For our reason for the assignment to none relates to Python's mechanism for reclaiming unused space. Internally, Python maintains a count of the number of references that exist to each object. If that count reaches 0, the object is effectively inaccessible. Thus, the system may reclaim the memory for future use. Since we are no longer responsible for storing the DQ'd element, we remove the reference to it from our list as to reduce the element's reference count. Got you. So this is just saying that the reference is replaced with none to free up that space in memory as well. And so also that we don't shrink our list repeatedly to, also have our queue basically be removed in memory and to have that wraparound effect be void. We need to keep that length. The second significant responsibility of the DQ method is to update the value of the underscore front to reflect the removal of the element. Right? When you remove an element, you need to update front to the next index value that is the next one to the right of the removed. And the presumed promotion of the second element becomes the new first. In most cases, we simply want to increase the index by 1, but because of the possibility of a wraparound configuration, we rely on a modular arithmetic as originally described in page 242. Resizing the queue. When enqueue is called at the time when the size of the queue equals to the size of the underlying list, we rely on a standard technique of doubling the storage capacity of the underlying list. In this way, our approach is similar to the one used when we implement a dynamic array. When enqueue is called at a time when the size of the queue equals the size of the underlying list, we rely on a standard technique for doubling. So if you have a queue that ends up maxing out the pre-allotted queue, you do dynamically increase by double. Gotcha. However, more care is needed in the queue's resize utility than needed in the corresponding method of the dynamic array class. After creating a temporary reference to the old list of values, we allocate a new list that is twice the size of the and copy the references from the old list to the new list. While transferring the contents, we intentionally realign the front of the queue with index 0 in the new array as shown. So if the front was originally at E in our old array that was maxed out, we subsequently would like to just make this easy on ourselves and take E, place it at index 0, and start from there. Basically start fresh with a new dynamic queue. The realignment is not purely cosmetic, since the modular arithmetic depends on the size of the array. Our state would be flawed had we transferred each element to the same index in the new array. Yeah, because we're using that modulo. Okay, we're getting there, but okay, I'm gonna do this last page here. Shrinking the underlying array. A desired property of a queue implementation is to have its space base usage be big theta of n, where n is the current number of elements in the queue. Our array queue implementation, as given in code fragment 6.6 and 6.7, does not have this property. It expands the underlying array when enqueue is called with the queue at full capacity, but the DQ implementation never shrinks the underlying array. As a consequence, the capacity of underlying array is proportional to the maximum number of elements that have ever been stored in the queue, not the current number of elements, right? If it never shrinks, it always will remain proportional to the max elements within its life cycle. We discussed this very issue on page 200 in the context of the dynamic arrays and subsequent exercise. See these ones in of this chapter. Okay, we discussed this very issue. Got you. A robust approach is to reduce the array to half of its current size whenever the number of elements stored in it falls below 1/4 of its capacity. We can implement this strategy by adding the following 2 lines of code in our DQ method just after reducing the size in line 38 to reflect the loss of an element. So if the size is between 0 and the length of data floored by a value of 4, we're going to resize by half. So this just takes our we still have a little bit of buffer room, a quarter amount of buffer room, but we just shrink our queue down, queue capacity down, basically. Um, Analyzing the array-based queue implementation. Table 6.3 describes the performance of our array-based implementation of the queue, ADT. Assuming the improvement described above for occasionally shrinking the size of the array with the expectation of the underscore resize utility, all of the methods rely on a constant number of statements involving arithmetic operations, comparisons, and assignments. Therefore, each method runs in worst case O of 1 time, exception for NQ and DQ, which have amortized bounds of O of 1 time, for reasons similar to those given in section 5.3. Right, because yeah, exactly. Like the NQ and GQ occasionally have that O of N runtime that happens, but we're amortized to O of 1 because we have many more operations that happen in O of 1 compared to that O of N operation of the dynamic increase or decrease of the Q array size. Cool. All right, this is going to be a good place to stop the learning for today. I really appreciate you guys joining me for today, but unfortunately, I have to call it short for today. I know I usually do over about 2 hours a day, but today is just one of those days where I have to call it short. I need to start heading out. I got to start heading out for holiday travel. I did want to pop in and spend at least like an hour and a half with you guys and just to learn something today, keep refreshing my skills and memory. As long as I just keep that these concepts fresh, it'll keep solidifying and compounding on one another. I just didn't want to, and I also wanted to keep the streak alive. So I really appreciate you guys joining me for today. Again, if you guys could follow the channel, it would be really appreciated. I really enjoy talking with you guys, and it just means that I get to talk with you guys more, and you guys can come back and connect with me in the future. Join the Discord. I provide all of my learning from Python Crash Course, DSA that we're currently reading, Fluent Python, this PDF book that we'll eventually get into. I am going to have all the information regarding CS50X that we're going to do. This is all the information regarding CS50P that I did. I'm going to add some more stuff regarding this for the actual regarding the solutions to my problem sets and my final project. And then we have a project showcase that we have some members that have added to, right? And then we just have some general Discord stuff. But join this if you wanted to get access to that. Like I said, in the new year, we're going to be starting up the new rendition of Harvard CS50X, which will be the more full stack type of overview, going over, from Python to SQL to Java to front end, back, all that kind of thing. And so hopefully at the end we'll be able to actually make some full stack applications and incorporate our current knowledge and maybe incorporate our task tracker, our small business manager into a more user friendly environment rather than like a CLI environment for future updates, right? So it's going to be great. So we're going to go through and watch those lectures together through a live watch along. We're going to make sure to get I'll put instructions, but we'll have have everybody get their account set up, and so we can all do it together, and it'll just be really easy format to join along and follow along together, rather than do it alone and on your own. So join the Discord if you want to get that access. I'll be coming out with that probably this week, starting announcing that. And then, yeah, we're almost done with chapter 6 here. We got a couple more chapter 5 problems to continue with at the beginning of the streams. And then we'll obviously have chapter 6 problems when we finish this one, and then jump into chapter 7. And little by little, we're over halfway done with the book regarding chapters. So really, really cool. We're little by little making our way through this and learning a lot along the way. I'm sorry I had to cut it short. Like I said, I'm going to start traveling for the holidays here, but I will be doing streams over the holidays. I'm going to try my best to keep the streak alive and stream on Christmas and stuff for at least like an hour and a half. I really want to keep it alive and talk with you guys and commit to this and show you guys that we are committed. So anyways, I'll see you guys tomorrow. Thanks so much for the love today, and again, I'm sorry it's short, but I'll be back tomorrow.